Okay, so I need you to recall all the way back at the beginning of the year, we talked about what an atom looks like. Yes? Yes, and you probably have some sort of image like this in your brain. Is this accurate? Absolutely not. First of all, the electrons don't have these nice, tracks to run around. Not only that, they're not even in one place. Electrons are in multiple places at one time. So, like, the idea of saying that the electron is here is pretty dumb. Electrons are actually, not only can they be in multiple places at once, they are almost always in multiple places at once. That seems counterintuitive to you, but here's the fact of the matter. Your brain did not evolve to have common sense about quantum physics. Your brain evolved to have common sense in the macro world. If you had evolved on this scale, it would just be totally normal for things to be in two places at once. Anyway, that was a weird aside. But electrons are the reason why things happen in chemistry. We've talked about this with valence electrons. This should ring bells. Covalent bonding, that should ring more bells. And ionic bonding. Yet again, your meat computer library should be lighting up with different areas of your brain where it says, I remember this, okay? Ionic bonding, covalent bonding, valence electrons, all of that has to do with where the electrons are and what kind of electrons and what kind of electron bonding the atoms want to do. You'll also recall from last time when we talked about alloys and metals, or 2 times ago, alloys and metals, that metals want to share their valence electrons, right? Well, today we're going to learn about electron configuration, which is looking at what the electrons are doing in the atoms, okay? So if we look at this, if we look at, again, this is going to be very confusing to you for a little bit. Don't worry about it. You will get it, okay? Electron configuration, all right? In your notes, I want you to draw your periodic table split up into these different sections. The leftmost 2 columns, just do like boxes. Just a box that is this shape, okay? A tall rectangle. Box that is this shape. A long, kind of wide rectangle. And then this shape, okay? Do not include helium. We'll talk about helium, it's a weirdo. So we have this shape, that shape, this shape. Don't worry about the lanthanides and the actinides down here. They are also strange. We don't need to worry about them right now. I just want you to focus on this rectangle, and this rectangle, okay? All right. Dmitry Mendeleev was the scientist that came up with the idea of the periodic table. And if you don't remember our boy Dmitry, he was an interesting dude that came up with the periodic table. He was a chemist, and I would say for his time, he was truly a genius. He looks like me in about 40 years after I have lost the will to teach anymore. He's got, well, I have a big forehead too, so there you go. Okay, Dmitry Mendeleev, he didn't just randomly say, Oh, well, I think that this should be the shape of the periodic table. He did this for a reason. Okay? He did this shape for a reason. This reason is because of the configuration of the electrons. Okay? So, over here we have the S bank, the D bank, P, and F. S, D, P, F. The electrons for each of these elements inhabit different shells and subshells. Okay? You'll remember the valence shell, right, which is the outermost shell, which for all elements except for hydrogen and helium, which are these guys up here, for all elements except for hydrogen and helium, you will remember that the valence shell can hold 8, right? It can hold 8 electrons. Well, there are shells underneath the valence shell, and depending on how many electrons it has in total, there are more. So these top ones don't have very many shells, but these bottom elements have a bunch of shells. And those shells are described as S, D, P, and F shells. Okay. The shells in which the electrons inhabit that are not the valence shell are called S, D, P, and F shells. Okay? When we do an electron configuration, and this is going to scare you, don't freak out. This is going to scare you, don't freak out. Oh yeah? Okay, we look at our good old pal, the periodic table here. No. What is going to freak you out is I'm going to do the electron configuration for something, and you're going to be like, what? And I will help you, okay? So let's do an electron configuration. Let's do it for manganese, which is this guy right here, Mn. Okay, we'll zoom in a bit. Okay, manganese, Mn. So manganese, I'm going to do the electron configuration for it. Mn. The electron configuration for manganese is as follows: 1, S, 2, 2, S, 2, oops, 2, P, 6, 3, S, 2, 3, P, 6, okay, 4, 4, S, 2. Everybody freaking out yet? 3, D. I know you don't. I'm going to explain it in just a bit. 3D, 1, 2, 3, 4, 5. 3D, 5. That is the electron configuration for manganese. Do I expect you to understand that? Absolutely not. I'm going to explain what it means. What? Is it above your pay grade? It is above my pay grade? No. Because I know what this means, and it's actually very important that I know what this means. Then I wouldn't be a very good chemistry teacher. Well, I would be an even worse chemistry teacher than I am. Okay. This, my friends, is counting electrons. Okay, what? We're counting electrons. How many electrons does manganese, element number 25, have? Within at least 6. If manganese is a neutrally charged atom, how many electrons will it have? Vince? 25. Why? Correct. The amount of protons has to be equal to the amount of amount of electrons. If you don't remember that, then remember it, please. I don't know what else to say. Okay? That this is the number of protons, and that protons are positively charged, and in order to have a neutral charge, you have to have the same number of electrons. If you don't remember that, it's I won't say it's okay, but I will say I understand that you have forgotten it. Remember it. Relearn it. Okay. So if we look at this, I want you to be paying attention to the supertext numbers here. 2, 4, 10, 12, 18, 20, 25. I want you to watch. 2, 4, 10. I'm just adding. 12, 18, 20, 25. We're counting electrons. So your question is now, what in the crap are these? Those are the shells. Okay, these are the orbitals of the electrons. This is the innermost electron shell, 1s. Okay, 1s. 1s is the innermost electron shell. So if we have an atom here, let's say we have an atom of helium. This is the nucleus. Okay, this is the nucleus. Around the outside, around the outside, around the outside. If you don't understand that reference, then listen to more Eminem. Okay, around the outside, we have 1 electron. This is helium, 2 electrons. They inhabit a shell called the 1s shell. This is helium. Helium has 2 electrons in the 1s shell. Okay? All right. Helium is over here, but I have seen many periodic tables that actually put helium both here and here. Because helium exhibits the properties of a noble gas, but its final shell is the 1s shell. So it is in this square. Remember when I had you make those rectangles and label them S, P, D, and F? Remember when I did that? Oh, you don't remember that because you weren't taking notes? No, I'm talking to Robbie.
Yeah, I feel like that's something.
That's fine. But I would like you to literally draw a square, okay? Or not a square, a set of rectangles that look like this. Okay? Long, tall one, squatty one, squarish one.
You don't want the one on the bottom.
Don't worry about the one on the bottom. The F's are weird. I want you to draw this, okay? Oh, that's a nice rectangle there, Mr. Croshaw. Thank you, class. I mean, it's okay. S. What's this one over here? P. And this is what? D. Okay? All right. So, we're going to do some simple ones. Let's do the electron configuration for lithium. Okay? Lithium. How many electrons does lithium have? Come on, guys. No. That's mass. This is mass. This is number of protons. If it is neutrally charged, the protons and electrons are equal. I will always assume that it is neutrally charged. Okay? Lithium, Li, has 3 electrons. So every single element has at least 1 electron in the 1s shell, because that's what hydrogen has, right? We have 1s1, 1s2. Again, I think that helium for this purpose should be over here. 1s1, 1s2. Okay? Lithium is 2s1. Lithium is 2s1. So if we were to write out the electron configuration for lithium, it would be 1s2, 2s1. That's it. It has 3 electrons. It has 2 electrons in its 1s shell, 1 electron in its 2s orbital shell. You can use them either way. It's technically more correct to say orbital. Okay? 2 electrons in the 1s, 1 electron in the 2s. Do you see how that works? All you need to do is read left to right. Left to right. 1s, 1. 1s, 2. 2s, 1. 2s, 2. Then we get to 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. Okay? And then we come back over here. 3s1, 3s2. 3p1, 3p2, 3p3, 3p4, 3p5, 3p6. Hilarious.
Thanks.
C, 3p, O. Hilarious, Mr. Croshaw, I know. Thanks, Leighton.
Yeah, rhyme.
What did? I don't know.
Wait,
I don't know. I didn't hear a rhyme, but it's very possible there was a rhyme in there somewhere.
Or I could be.
Pele. He scored over 1,000 goals. Sure. Messi's up there. Cristiano Ronaldo's up there too, but Pele was something else. Anyway, of course, he played in a different era. It's like comparing like Wilt Chamberlain to like LeBron James. They're two very different players because the era that they play in is very different. I know, but still, very different era. Anyway, why are you asking me this? Anyway, shows how much you're paying attention to chemistry. Okay, 1s, 1, 2s, 3s, 4s, 5s, 6s, 7s. Do we see how that works? Yeah. Okay. The D's are a little bit strange in that the 3D is not in the third row. It's in the fourth row. But just remember that the middle here starts with 3, not 4. So it's 3, 4, 5, 6. You're probably still confused, at least a little bit, many of you. You're gonna get it, I promise. Okay, let's do the electron configuration. Let's do the electron configuration for phosphorus. Okay, let's do the electron configuration for phosphorus. And I want you to do this with me. Okay, so phosphorus is this guy. All right, phosphorus, which is chemical symbol P. That is not a very good P, but oh well. Chemical symbol P. So how do all electron configurations start? 1, S, 2, very good. Why? Because it has two electrons in its 1s orbital, which is the closest one to the nucleus. Right? So now we can just count over. So 1s1 would be hydrogen, 1s2 is helium. Okay? Where do we go from there? What is lithium? What row is it in? It's in the second row, which means it would be what? 2. And what area of the periodic table is it in? S. Right? So we have lithium and beryllium next to them, right? There are 2 electrons there in that S orbital. We are. Just look at the periodic table. All you need to do is read left to right. Because phosphorus is after lithium, yes? So we have to go through all of the elements to get to phosphorus to count up the electrons. Does that make sense? What comes after beryllium? Boron, yeah, just the B there, right? What rectangle is boron in your little diagram? P. What row is it in? 2. 2. P. How many electrons are in the 2p orbital? Let's count them. Yep. 1, 2, 3, 4, 5, 6. I know it's not. We are reading left to right to get to phosphorus. We have to start at the top, go left to right, count every element in between hydrogen and phosphorus. You need to be able to follow where the electrons are.
So that's why it's more.
Yes. So as we go left to right, we get more electrons, right? Okay. So 2p6, because there are 6 electrons in the 2p orbital, right? Because, and the way that we can establish that is this is the 2p area, right? And there's 1, 2, 3, 4, 5, 6 elements in the 2p area. Cool? Hell yeah. Okay, where do we go next? We go to the 3s. Very good. 3s. How many electrons can be in an s orbital?
2.
Only 2. S orbitals can have a maximum of 2 electrons. Okay. Now, so we're here, 3s2, right? So we got this one and this one. Now where do we go to phosphorus? 3 what? 3p3. 1, 2, 3. 3. 3p3. Thumbs up. This is the electron configuration of phosphorus. And if you are not sure if you did this right, what can we do? Add them up. Very good, Shelby. So how many, you can ask for help, but I want you to be independent. I want you to be a strong, independent boy. Okay? How many, no, you're not. You're a child. You're still a child. Robert, you are still a child. Can you sign a legal document for yourself? No. You can, and then the person will laugh at you and say, ha ha ha, no, because you're a minor. Me. All right. So how many electrons should phosphorus have?
15.
15, because it is equal to the number of protons, right? So if we did this right, we should be able to count the superscript up to 15. 2, 4, 10, 12, 15. Success. Okay? Let's do another example before we get to the next principle. Yes, Davis. You may go to the restroom. Let's do nickel. Nickel. Nickel is kind of farther along, right? So where are we going to start? Up at the top left, which is what? 1, s. S orbitals can hold 2 electrons, 1s2. Now where do we go? 2, s, 2. Now where do we go? 2, p, 6. Okay, so where are we now? All right, so we did 1s2, 2s2, 2p6. Now we're here. So this is what? 3s2, 3s2. Okay. Now where do we go? You're good. 3 p. Yeah, remember the p orbitals can hold up to 6. 3p6. So we did 1s2, 2s2, 2p6, 3s2, 3p6, right? Okay. Now we go to 4s. 4s. How many electrons can an s orbital hold? 2. Okay. Now we get into the d orbitals. Right? D, but we're not doing 4d because remember, d is a little bit weird. It starts at 3. So we're going to do 3d. How many electrons in this d orbital if we're doing nickel? 1, 2, 3, 4, 5, 6, 7, 8.
Wait, so why
It's a little bit strange. The transition metals. Transition metals, yeah, they're just weird. Oh, what? Shoot, what? Okay. Okay. The transition metals start at 3D. I don't know why. It has to do with quantum. That truly is above my pay grade. Quantum physics, quantum chemistry is way beyond what I understand. Trinity. Okay, that is one heck of an electron configuration, and we aren't even close to being done with the periodic table. We're in the first. Just a second. We're in the first row of the d orbitals. Imagine if you had to do the electron configuration for silver or for mercury. Oh man, that sounds terrible. No? Emma?
So in the second row of
This here, the second row of the d orbitals is 4.
so it's just one less.
It's just one less. The d orbitals just start back 1. I know it seems strange. I don't really understand why it is either. I do not have any food. So the reason why it looks the way that it does is because this is the way the electrons actually line up in nickel, and this has to do with why transition metals like to share valence electrons. You can see here that this is a little bit backwards. Nickel fills in this, and then it fills in this, and then it fills in this. This is a combination of the p and d orbitals, and then it adds on the last 2 s orbitals last. That's why it's 4s. That's why it's 4s, 1, 2, 3, 4. Does that make sense? That's why it's 4s2. The s orbital electrons are actually its valence electrons. Seems very strange. I'd love some. Let's go with the polar ice. Let's do like 4 of them, please. Thanks, pal. Okay. So that seems like one heck of a thing to write out. If I asked you to write out the electron configuration of nickel, I'm guessing that you probably wouldn't want to write out this entire thing. What? Why not? I don't know. You tell me. Why wouldn't you want to write it out? Because it's long, dude. 1s2, 2s2, 2p6, 3s2, 3p6. Let me show you a very extremely handy shorthand. The electron configuration of nickel can be fully written out like this. You can also use the shorthand. The shorthand starts at the last noble gas, which in this case is argon. And this is how you do it. You started the last noble gas, and you put that noble gas in brackets. You have just skipped all of that. The electron configuration of argon is 1s2, 2s2, 2p6, 3s2, 3p6. We have just skipped all of that. The electron configuration in shorthand of nickel is argon 4s2, 3d8. Okay? So when you want to write the electron configuration of something that has a mega long electron configuration, all you have to do is go back to the previous noble gas. So go backwards from where you want to be and go to the previous noble gas. Let's see how that works. Okay? If we choose to do the electron configuration for antimony, which for Latin reasons is the symbol Sb. Antimony, Sb, which has 51 electrons for a neutrally charged atom. And we don't feel like writing the entire electron configuration for 51 electrons. So this is the electron configuration for antimony, Sb. What is the previous noble gas for antimony? What is the previous noble gas? Krypton, Kr. Okay? Krypton, we put it in brackets, K. If you need to do the electron configuration for a noble gas, choose the previous noble gas and then do the electron configuration of that. So you'll have to do the entire row essentially of the noble gas. The electron configuration for hydrogen is 1s1. Okay?
You said everything starts with the 1s2.
Everything starts off with 1s1 at least. Okay? So krypton, what if we are starting at krypton, what do we do now? So we started here, so what do we do now? Good job, Leighton. 5s2. 5. I'm going to try and make this 5 not look like an S. S2. Okay? 5s2, and then what? Oh, crap. Yeah, it would be 4s, or sorry, 4d, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 4d10, 5p3. Yeah, tell you can do it. What did you want? The other one? Okay, let me pull it up.